Web Systems Week 8, Part 2, Advanced Logic. Previously we learnt a little bit about logic and, or, and not gates. Today we're going to look at a bit more complicated expressions and how to simplify them, especially since we need to be able to do two important tasks: write the logical expressions and to work out when two logical expressions mean the same thing. And the best way to do that is to simplify things. Now, with Boolean logic, there's various laws you have to follow. Obviously, rules like and, ors, and nots. But there's a few more rules you have to follow very carefully. And these basically are, and these are the ones that you'll be examined on: associativity, distributivity, the complement law or identity law, commutativity, and De Morgan's laws. We'll go for these one at a time and see their relevance to solving and simplifying these Boolean logic equations. So the first law is Boolean associativity. And reality is it might look like a fairly complex rule, but it's really simple. It simply says if you have the same logic expression, in this case it's and, you can shift the brackets into any position. So x and y and z is the same as x and y and z. Same thing with or. X or y or z is the same as x or y or z. In other words, if you say something like red or green or blue, it doesn't matter which order they are in. So the most important thing to be aware of this rule, it's very much like mathematics. If you have a plus, you can mix plus signs anywhere, or multiplication signs. You cannot mix the ands or ors. It's just like arithmetic, where you can't really mix the pluses and multiplications. Fairly easy rule to remember. So here's an example in arithmetic. A times B times C is the same as A times B times C, or you can get rid of the brackets altogether. A times B times C. The second rule, distribution, simply means and has priority over or. Keep that in mind. So the ands are the most important parts of an and or Boolean logic equation. So here's an example. If you have x or y and z, you effectively convert the expression to adding the and z to both halves of the equation. So it becomes x and z or y and z. Okay? The and z is distributed over each of the or statements. Same thing with or, it's the opposite way around. If we have an or anding, we could do the same thing. X or z and y or z. Okay? Keep that in mind. I'll show you why. Let's look at it like it was arithmetic. Remember, treat the ands as multiplications and the ors as pluses. So a plus b times c is the same as a times c plus b times c. Remember, that's an and, that's an or. Very easy, intuitive rule to follow. A few things to be very careful about. It's not exactly the same as arithmetic. And there's a few things that you'd be very careful about. With ands and ors, computers don't necessarily have priority. For example, in some languages like Java, this x and y or z might be valid, but in other languages it may not be. So just be careful. If you have a and y or z, it's an ambiguous statement, hence it's not valid. For example, x and y or z is not the same as x and y or z. Remember the rule? Don't mix the ands and the ors together. Simplest way to check, just plug in false, false, true. Plug it in, you get different results at the end. Now, natural numbers have issues as well, so don't just be careful following that rough rule of thumb. For example, logic, I've already said x or y and z is equivalent to x plus y times z, effectively, if you look at mathematics. This rule's the same rule, but it doesn't work the other way around. X and y or z, okay? In other words, x times y plus z is not the same as x plus y times, open bracket, y plus z. So keep that in mind. It's not exactly the same as math. Just keeping careful track of the exceptions to this rule. So you can almost treat AND as multiplication and OR as plus, except in this situation. The complement rules are very simple. An observation. With OR statements, everything is true unless both are false. In other words, if you OR anything with true, it'll always end up being true. If you OR anything with false, you can simply discard the false statement. It'll always be this value, x. Big difference to multiplication. Same thing with ANDs. X and true is always going to be true, just x itself. And x and false always becomes false. It's like multiplying by 0. So just to repeat, if you have an x or true, you can chomp out the x. If you have an or false, you can chop out the false. It's like adding 0. If you multiply anything by 1, it's always going to be the same thing. And if you AND anything, multiply anything by 0, it'll always be false. So the key thing is, there's an important rule that if you see a word that looks like this, x, so an expression, x and not x, it's always going to be false. In other words, you can't have contradictions. Now, De Morgan's law is the final one to think of. And this rule simply says, if you not something and you OR it, and you not another expression, you can change the bracket so it's not P and Q in this particular case. All you do is you make the sign the opposite one. So we convert the ORs to ANDs and put the nots in brackets. Ditto with this side. We convert the ANDs to an OR and put a bracket around it. That's all we need to do. So let's try an example in real life. Okay, so here's a question. What do you have for dinner? Well, our answer could be, we said not pizza and beer. What does this mean? I didn't have pizza, or I did have pizza. Did I have beer, or didn't I have beer? Well, what I actually mean in this particular statement is, I didn't have pizza and beer together, which of course seems like a contradiction, but, well, this example, I didn't have pizza and beer together, which is also another way of saying, I didn't have pizza, or I didn't have beer. In other words, I might have had pizza, or I might have had beer, but not the both together. That's all the rule simply says. Very simple, obvious type thing to set up, but it's very useful for simplifying logic. Let's take a look. The reason why we do De Morgan's is because you can effectively, it's been proven that you can simplify very complex Boolean equations. And if I go back a moment, a NAND gate, I call it NAND, is equivalent to not and. Okay, not and. It's called a NAND gate. So I reverse the inputs. It's the equivalent of an OR gate. You can prove that. When you're building a computer chip, it's easy to make billions of the same type of logic operation as it is to make multiple different types. So integrated circuits can be produced with far fewer gates to form the same functions. You simply need NOT gates and NAND gates to do virtually all the functions. Build everything out of small Lego blocks, and it's a very easy to make, very powerful and very complex integrated circuits and CPUs. So all you do is you connect these NAND gates and you could make logic functions. We'll talk about that in part 3 when we look at arithmetic. So let's try to put all these things in practice. You'll be required to simplify many expressions. Does A or not B an A? What does that equal to? Let's take a look. Well, first thing we see is the not A and B. We can expand that out using De Morgan's. That becomes not A or not B. Notice I flipped the ORs. And then we can do something like this. We can take the A or and not, the associativity rule. Then we can use the complement law. A or not A becomes true. So that our simple rule becomes or not B. But it happens that always ends up being true, because anything you OR, whatever the value is, true or false, ORs will always be true. So this is a classic case. If you have a if statement or a for loop, using that expression, it'll always loop or always go free forever. So when you're debugging a program, you'll find using logic can solve many problems in your code. So you'll need to use these laws to simplify logic in the exam. Good example to try: plug in ones, make sure trues equal 1 and falses equal 0. Make ands like multiplication and ors like additions. Just try that out and you'll find the answer becomes fairly obvious at some points.